So now that you've learned a bit about angular momentum, I wanted to show you a few example problems that will use some of the concepts that you learned in that video. So in this first problem, this is actually part B of a problem that's on your WebAssign from worksheet 5.5. And I'm going to lead you through most of the steps in solving this problem, though I will not give you an actual answer. Part of the reason I'm doing that is because the numbers that you see may be different than the numbers that you see on my screen here. But I'll at least get you most of the way there, and hopefully it helps you understand problems like this. So we have this ball that is being shot directly upward here, and we're asked for the angular momentum about point P, and you can see point P marked on our diagram there. This problem is one I wanted to look at because one of the things that I mentioned in the video about angular momentum that might seem kind of strange is that an object can have angular momentum even though it's not rotating. And that would be like this object right here. The main reason that we use things like angular momentum for things that are moving in a straight line comes in when we do problems with conservation of angular momentum, where perhaps something is moving in a straight line and then it hits something that will then rotate. But I wanted to do this problem to get a little bit of practice with calculating angular momentum for something moving in a straight line. So we know angular momentum for a kind of small object like we have here. This ball can be treated like a particle. L equals R cross P. And we're going to go the simple route of doing RP sine theta to give us the magnitude. Actually, I'll write that here since that won't have a vector symbol. And then we'll use the right-hand rule to come up with the direction of this angular momentum. So I know that linear momentum is m times v, so I'm going to write that in here. So to find this magnitude, we want to multiply rmv sine theta. We know mass, that's a super easy one. When it comes to r is considered the distance from point P to where your object is located. So right now, this is your r vector. Let me switch to a different color here. This is your r vector. When my ball is a little bit higher, so let's say when my ball is up here, this is my r vector. If it were up top like that, that would be my r vector. So you may be noticing a couple of things. For starters, one of the big things that you may be noticing is the fact that the length of that vector that I just drew is getting longer and longer. Another thing to notice is that the angle is changing, because remember that this angle theta in this equation is the angle between your r vector and your velocity vector. And so my velocity is pointed straight up on the way up and pointed straight down on the way down. And so that angle is going to change as well. But it actually brings up a point that we talked about in torque, the idea of the moment arm. So one way that I could write this magnitude is mv times the quantity r sine theta. And basically this quantity r sine theta is going to give me the component of r that is perpendicular to my velocity. The reason that we care about that is that component of r that's perpendicular to velocity is always the same value. My velocity is always up or down. So when I'm looking at the component of r perpendicular to it, I'm always looking at the horizontal component of r, and that's going to be a constant value of 2 meters. Or at least in the problem that I have here, it's 2 meters. It might be different in your problem. So that becomes really convenient because even though my length of r and my angle is changing as this ball rises up or falls down, the value of that component is constant. And so I'm going to have a constant angular momentum. So to finish off this problem, I'm going to multiply that mass of my ball times that distance between point P and where the ball is initially located. And then I'm going to have to find V. So one of the things in this problem, the reason I chose part B, part A asks for the angular momentum at the maximum height. And so you'll have to figure out the velocity at that maximum height. Part B of this problem asks, it's actually where it's halfway back to the ground after meeting its maximum height. And the only difference between these two is the velocity that you'll plug into the equation. Calculating the velocity is going to require some knowledge from previous units. Specifically, probably the easiest one to use. Actually, you probably could use conservation of energy, or you could use kinematics because this ball is in free fall. So it gives us a little bit of practice with some of our prior units. And once you have that velocity, you're just going to plug it into this angular momentum. I wanted to look at one other problem that is a little bit different from this. In this case, we're going to use a different definition or a different way of finding angular momentum, because this time we have a disk that's kind of rotating like a merry-go-round, and it has a torque that varies. And so we want to find the angular momentum at 3 seconds. So in the video, you learned, one of the things that you learned was that torque is equal to dl dt. That was really similar to our linear version, that force equals dp dt. And this time we're given a torque and we're looking for angular momentum. And so as we've learned in the past, if we kind of want to undo a derivative, we use an integral. So my angular momentum is going to be equal to the integral of torque with respect to time. So I have an expression for that torque. And my expression says that it's 5.00 plus 2.00 t Newton meters. And then we're going to integrate with respect to t. And it also kind of gives me some information at t equals 1 second. There's its angular momentum. What's its angular momentum at 3 seconds? We're going to use this information to help us figure out the plus c once we integrate. So let's go ahead and integrate first. The integral of 5 would give me 5t. The integral of 2, my decimal point's kind of lost there. The integral of 2t is going to give me t squared, and then plus c. So that's my expression for the angular momentum. And it says that the angular momentum is equal to 5 at 1 second. And so I am ignoring units right now. Pretend like I'm not ignoring units, but I am ignoring units. So I have 5 times 1 plus 1 squared plus c. And that tells me that c is going to be equal to -1. So my overall expression for my angular momentum is 5t plus t squared minus 1. And notice how they kind of cheated with the torque where they put units at the very, very end here. We could kind of do the exact same thing. So my units here, this is one of those that I typically don't memorize the units of my angular momentum, but I think it through with the equation. So one of the ways that we find it is r cross p. And I know that momentum is kilograms meters per second. So this is going to be kilograms meters squared per second. And so I can plug in my time at 3 seconds. And that should give me 23 kilogram meter squared per second as my value for L. As far as it comes to direction, I'm not given much information about the direction of that torque. As a matter of fact, I just noticed that that torque was given to me as a magnitude, not as a vector. So even though it doesn't ask for the magnitude of the angular momentum, I'm not given quite enough information to be able to come up with that magnitude is. So it's whatever the same direction as the torque is at that point. So hopefully this helped you kind of see some examples of some of that concept about angular momentum that we learned about.